So I'm returning 2 items to you today, the quiz, and half of you have not received the AA lab report yet. So, and that was because I was super late. So everybody gets a candy attached to their lab report. Now yeah, the ones that got it already, they don't get a candy. Well, I have all of Halloween candy with me today. And the reason I have it, and Chelsea went to grab the participation sheet, is some of you are not participating enough. So today, in addition to +2, you get a candy. But it has to be a worthwhile participation.
No, +1?
+2 for participation, yeah.
Do we get a reward for participating?
Participation point is a...
There's always one.
I don't remember now. You're confusing me. Well, in addition to the participation point you'll get a candy. I lost everybody. Okay, so that's the deal today. But as soon as Chelsea gets back, we will hand out. Okay, so the quiz. Everybody did pretty well in general. That's a good distribution. Okay, so as soon as Chelsea's here, you get stuff back. And as I said, by end of today, I should have all the grades up till now updated on Moodle, except for extra credit. You won't see that yet. Okay. All right, let's continue where we left off last time. All right. So we were talking about dietary fiber, and we left off at how do we determine dietary fiber. So we start off with a pre-dried and fat-free sample, and we need to solubilize everything but the dietary fiber. In order to do that, we use a bunch of enzymes. So alpha amylase, we digest with alpha amylase to break down starch. We digest with protease to break down protein. And there's here a note. We heat the sample so that the starch is gelatinized, so that the enzyme can digest it, especially if we're starting with a material that is raw ingredient, like wheat, for example. We want to determine the dietary fiber in wheat, so we have to make sure that the sample is heated so that starch is gelatinized, so that digestion will be faster and more efficient. And then the other enzyme that we add is the glucoamylase, which is the exoenzyme that will break one glucose unit at a time. So ultimately, we want to make sure that we don't have maltodextrins or large saccharides in there that might precipitate. So we want to make sure that the protein is soluble, the starch has been broken down, so that everything is in the soluble. So we definitely have to control pH, temperature, and time because you have enzymes. So you have to select the optimal pH and temperature for the enzymes to act and ensure hydrolysis. At this step here, step C, after digestion with glucoamylase, we can precipitate the entire fiber, the soluble and insoluble. So we can add ethanol, wash it multiple times, filter, and get all of the dietary fiber, the soluble and non-soluble. And we'll get total dietary fiber in one shot. But definitely, we always have to correct for protein and ash. Ash meaning the minerals. The minerals might precipitate with your fiber. You don't want to count them as fiber. So we take the sample, we analyze protein and ash, subtract that from the total weight, because it's a gravimetric measurement. So you take the weight of whatever gets filtered out when you precipitate with ethanol, and that would be your dietary fiber after you subtract ash and any residual protein that did not get hydrolyzed and removed. Okay, so that would be your total dietary fiber. Now, if we do not wash in this step here, if we say, okay, I want to quantitate soluble and insoluble, both. If I precipitate everything, I cannot differentiate. That would be my total dietary fiber. But soluble fiber, pectins and hydrocolloids, will remain soluble with your hydrolyzed starch and protein. So if we filter, you will end up with two portions, the solubles and the residue, the insoluble. So if we look at the residue, it's after you filter, you end up with the residue. At this point, this is insoluble fiber. We wash it with water, ethanol, and acetone to make sure that we take out any residual solubles out of it, and then dry, and then you weigh. Again, it's a gravimetric method, so you take the weight of that, but we have to correct for any residual protein that precipitated and any ash that remained in the sample, because you don't want to count them as insoluble fiber. So you take that sample, you determine protein and ash, and you calculate your insoluble fiber. So that's the residue. Okay, so if we go back, here you have your starch broken down to glucose, protease broke down your protein, it's soluble, you have the soluble fiber with it. When you filter, you end up with a residue, and then the soluble fiber is still with your solubles. So we've done the residue, then the filtrate that goes through the filter and doesn't get retained on the filter includes the soluble fiber, but it includes everything else. It has the glucose and the peptides from hydrolysis of the protein, so you want to remove the soluble fiber. At this point, you precipitate with ethanol. Great, found it. Thank you, Chelsea. All right, let's have a look. Okay, some of you are done. We have up to 15 participation. Each participation is worth 2 points. And we have people that haven't said a word the entire semester. What? Okay. Today is the day. All right. Oh, okay, I'm going to give it to Chelsea back. Yeah, I'll put that. Thank you. All right. So to separate the soluble fiber from everything else that was solubilized, then we add ethanol. So then now your soluble fiber will precipitate. You filter that. Whatever remains on top of the filter is your soluble fiber. Several washes to make sure you get rid of any residues. Let them go through the filter. And you take what's left on the filter, you measure protein and ash to correct for that, so that they don't count as soluble fiber, and then you measure the final weight. This way you can get the insoluble separate, the soluble separate, you can add them and then get the total soluble fiber, total fiber, sorry. So that in this way you have the amount of insoluble, the amount of soluble, add them together, you get the total. So there are other ways of determining total fiber that is not based on gravimetric analysis. In this case, you want to look more into the identity of these soluble fibers. What are they made up of? Are they pectins, or are they certain hydrocolloids, or cellulose, hemicellulose? So you want to go back and determine the monomers. In order to do that, you do the same sample preparation. That's the Inglis-Cummings method. It's the GC method. But you do the same preparation step. So you gelatinize starch, digest by enzymes, same way. Protein, you hydrolyze. And then the remaining non-starch polysaccharides are hydrolyzed by sulfuric acid. So now we break them down to monomers. by strong sulfuric acid. So we get the monosaccharides, and we do GCFID, gas chromatography, flame ionization detector. However, uronic acids cannot be detected with GCFID. You do a separate, uronic acids are the, what are the uronic acids? Where are they? Do you remember? Which dietary fiber is made up of galactouronic acids? Have you talked about that in food chemistry? No? You didn't do carbohydrate fiber? Pectin. So the pectin, the monomers in pectin are galactouronic acids. So they won't be determined by GCFID. You do a separate assay, colorimetric detection, just for the uronic acids. So analysis of pectin that is gravimetric is usually done when you know that you have nothing else but pectin really, like jams and jellies that pectins are used as a gelling agent. So in order to, you cannot break glycosidic linkages. It's very hard to break the galactouronic acid, this linkage here, galactouronic acid glycosidic linkage. So hard to hydrolyze with acid. So there is what you do is you do a saponification with NaOH, similar to saponification you've done in the lab. What this does, it breaks off this ester group here, the methyl group. Gets cleaved off, and you end up with carboxyl groups that are negatively charged. You add calcium. The calcium will result in precipitation because you will have cross bridges now, calcium bridges between, because the calcium is positively charged, will react via electrostatic interactions with the negatively charged carboxyl groups, and you form big polymers. They precipitate, filter them out, calcium pectate that is, and measure the weight of it. So you would determine pectin that way. Okay, so this is something I would like you to solve for extra credit. Since we're not doing, not now, homework, bring it back on Friday. It's for +5, okay, not +2. It's +5. I want you to learn how to do that since we're not doing dietary fiber in lab. So basically, we collected data on dietary fiber, insoluble and soluble. Crucible is basically a unit we use to filter out the sample. So it will be, we will have pores, and then we put a filter paper sometimes on it, depending on the pore size of the filter. And then you basically hook it up to vacuum pump. So you will have vacuum here to help with suction and filtration that goes fast. So this crucible here is where we collect the fiber. We filter everything that is soluble will go out, and you take the crucible, you dry it, and then you measure protein and ash, and then you take the weight. You take the weight and then measure protein and ash in the sample, and then you correct for that to determine the total amount of insoluble or soluble fiber. So you will have 2 replicates here in this example, 2 replicates. And this is the weight of the crucible empty. Here's the weight of the crucible with the residue. After you filter, you will end up with the residue. So the difference of that will be the insoluble dietary fiber yet not corrected for protein or ash. Okay, so you take that crucible and you do the ash, and then the difference will be the ash content. And this is the amount of protein. So you have to take that, subtract it from the difference here. Anyway, think through it yourself. And then we always run a blank because there might be any contamination of soluble and insoluble fiber in everything we do. So you would correct for a blank as well. So you need to, this is the information you need to collect in order to get the total dietary fiber. So please work on it. Work on that exercise for the extra credit, and I'll post the key on Friday after you turn in your that sheet. Okay, so that's it for total carbohydrate. I will shift to enzymes. Yeah. Oh, it fell off? Yours fell off?
No, I guess.
If you haven't gotten your AA yet, you get a treat. Okay. All right. Shifting gears. Starting a new topic. Applications of enzymes in food analysis. In food chemistry, you talk about enzymes, you learn about them. Here, we talk about applying these enzymes for the sake of analysis. But there will be some refresher information that you learned in food chemistry so that you understand how we design enzymatic assays that will help us in using them in analysis. Okay, here are some pictures that you see. What prevents the sugar from crystallizing in sherry-coated chocolate? First candy. What do you do? You know, if you add sucrose and you leave it over over time, the sucrose will crystallize.
Do you add fructose corn syrup?
No, but you still get the candy because you tried. Okay, Ted. Invertase enzyme. So an invertase enzyme is used to break down sucrose into fructose and glucose. Fructose will not crystallize, well, take a very, very long time to crystallize. Glucose will crystallize, but will take much longer time. So you will have the syrupy syrup without crystallization over a long period of time. I can't reach Ted. Let me try. Okay, I'm glad I didn't hit anybody. Ali took cover. All right. Milky Way. Next. All right. Where do we use enzymes or in different food systems, whether for analysis or not for analysis? What are different applications or uses? Yes, Billy? Clarifying juice. All right. So yes, so for clarifying juice, so it's like processing aid, we call that. So processing aid, that means we use pectinase to clarify apple juice. Okay. But in another application, we want to inhibit a particular enzyme to prevent separation of orange juice into clouds. So you know when you buy orange juice, sometimes you have to just shake it. So which enzyme we really want to inhibit to prevent sedimentation? It's not pectinase, it's something else. Pectin methylesterase. Because it removes the methyl group. By doing so in the presence of metals or calcium, let's say, it will cause polymerization of the fiber and precipitation. What else? Sarah?
Cheese making?
Rennet, yes, in cheese making. Again, processing aid, but again, we do use enzyme assay to test the activity of rennet. so that we know how much rennet we need to add to a certain amount of milk so that we produce a certain amount of curd in a certain amount of time. I was going to throw this at you. Why not? Good. Other than processing tool. All right, Claire.
You can check to see how done or how far along chemical or enzymatic reactions are for testing for enzymes such as alkaline phosphatase in
Alkaline phosphatase in
milk.
milk. This is actually done to test pasteurization. So basically, if you pasteurize the milk, instead of measuring microbes, which takes 2 days to do, you can measure alkaline phosphatase, which is thermally stable. If it's inhibited, that means all pathogens have been killed. Well, almost. Almost. What else? Lynn? Carbohydrate analysis, we just talked about that. Should I give her 2? Yes, so we use them. Yeah, she said yes. Yes.
Flavor?
Flavor. Expand.
Isn't it just why are enzymes important?
Yes. Can you give an example of an enzyme that may impact flavor?
Like in garlic, when you crush it, like that type of thing? Or are you talking about?
When your flavor goes bad sometimes.
Oh, like
Lipase,
lipase?
lipoxygenase. Good. All right. So food quality, processing tool, measuring activity like rennet. We talked about that. Sample preparation like carbohydrate, preparation for carbohydrate analysis, or even preparation for dietary fiber. We just use alpha amylase and protease to prepare the sample to determine dietary fiber. What is something else you didn't say? Specifically, we use enzymes in assays to determine constituents, right? Like glucose, for example, or sulfite. We're going to talk about that in a minute. So food constituents sometimes can be, many times we'll have enzymatic assays just to determine certain constituents. Waste management, I have it here because if you have waste streams that are, let's say, high in lipid and high in protein, they might block the pipes or block the waste where they go in the pipes. So they add enzymes to hydrolyze them so that they don't block the pipes. Okay, so the enzymes are important, basically. That's what it is. All right, a little bit of a review to help us understand certain concepts related to food analysis. So we have to review some concept you already learned about in food chemistry, but half of you already took that last year. So a little bit of refresher helps. Okay, so in enzyme reactions, you're basically reducing the kinetic energy so that you have a reaction going faster or facilitating reactions in general with lower energy. So the initial, what happens is your substrate will interact with your enzyme, produce the enzyme substrate complex, and the enzyme substrate complex will then, the enzyme will produce products. So you will end up with enzyme and product, and the enzyme is available again for use. So you have rate constant 1 that goes from E plus S to ES, rate constant 2 that goes from ES to E plus P, and rate constant -1 because this can go either way. ES can go back to E plus S or go forward to E plus P. So you have a stereochemical binding between the enzyme and the substrate, and then you end up with a conversion, a chemical conversion. That's the main events that happen during an enzyme activity assay. I'm sure you've seen this before. This is the plot of products versus time. So when you add your enzyme to a substrate in solution, what happens is you have a pre-steady state where it takes less than 1 second sometimes for the enzyme to bind to the substrate. We call this pre-steady state. After that, when you start seeing products generated, when you have the rate of disappearance of ES, this plus this equals the rate of appearance, which is K1. So at this, we call that steady state. At this point, it's a steady state, and you can see that it's mostly a linear curve. The slope of that linear portion during the steady state is your velocity, or the rate of the reaction. Or we call it V0, which is the initial rate of the reaction. So you can see that this curve plateaus. It plateaus over time. Why? Why does P plateaus over time? It's a Twix. Okay, Mallory, you raise your hand first. I do.
Because even if there's a lot of substrate, the enzyme can only work so fast.
It's not about fast. It's production of the product get reduced over time. But anyway, you get the Twix.
Oh,
Billy got the Twix.
are you serious?
Do you run out of substrate?
We run out of substrate, definitely. So she gets butterscotch. And another one. Okay. So you run out of substrate. So basically the rate of production of P will plateau. So that's why when you want to determine the rate of the reaction, you have to be working here. You don't want the reaction to go longer, then you will not be predicting the rate of the reaction properly. So familiar with these terms? Initial velocity, we said this is the slope during the steady state. And then you have maximum velocity, and you have the Michaelis constant. So maximum velocity, in this curve here, you have the velocity plotted over substrate concentration. So how do we get to this curve? Let me explain how you can plot such a curve. So you would run your reaction at a concentration, let's say, of 2 molar of the substrate, and then you run it at 4, and you run it again at 6, and then 8, etc. Every time you run the reaction, you monitor the product. Please put your phone away, or you can step out. All right, every time you run the reaction, you get a slope. And then you plot that slope over the concentration of the substrate you have used in that reaction. And then what you notice is when you have high concentration of substrate, you reach Vmax and it plateaus. That means your enzyme is saturated with the substrate. Okay? So you have provided abundancy of substrate that you cannot increase the rate of the reaction anymore. So you reach Vmax. So this is velocity of the reaction at very large substrate concentration. Now Km is a very important parameter in enzyme reaction kinetics. It's very important because it alludes toward the affinity of the enzyme to the substrate. So, and if somebody asked you, or in College Bowl they ask you, what's the definition of Km? It's the concentration of the substrate at Vmax by 2, or half Vmax. Okay? So it's the concentration of the substrate at half Vmax. If you have an enzyme and substrate 1, for example, I always draw this, but in a different class. So if you have S1, and then you have say this is S2. So you ran the enzyme with S1 and you ran the enzyme with S2, and then a different concentration, and this is V0, and this is substrate concentration, really. Okay, so then you get Km here, Km here. That's 1, that's 2. the enzyme has affinity to which substrate? More affinity to which substrate? Huh? Raise your hand. Go ahead, Brett. KM1, why is that? Yeah, it's true. Yeah, why? So substrate 1. So you reach Vmax2 at less concentration than when you have S2. You need higher concentration to reach Vmax over 2. So this means the enzyme has more affinity to substrate 1 than substrate 2. Okay. So different factors impact Km and Vmax. Obviously the pH impact because it changes the ionization on the active site, so it will impact how the substrate will bind. Temperature, because you need optimum temperature as well for the enzyme to act. Inhibitors, concentration of substrate. So all of these factors may impact the important parameters of the reaction. That's why when you design an enzyme reaction, you have to understand the impact of each one of those to achieve do you want to achieve Vmax? Do you want to have a high affinity? So you want to make sure that you get those conditions right for the enzyme reaction to work in the way you want it to. So these are very important terms that you really need to know. When you're looking at an enzyme reaction and you are after determining a concentration of glucose, let's say, substrate. So you care for the substrate, right? So you do not want the reaction to be first order. Well, actually, you want the reaction to be first order to the substrate. What does that mean? It means that you want a change in the rate of the reaction based on the concentration of the glucose, for example, that you're trying to measure. If you have concentration that is really high with relative to the enzyme, any change in concentration, you won't see a difference. So for quantification of a substrate, that won't work. So you don't want to have an abundance of a substrate to saturate the enzyme when you're actually looking at concentration of that substrate. So when you're looking at a concentration to measure a substrate, you want to make sure your substrate concentration is much lower than the Km. In this case, the rate of the reaction is dependent on the substrate concentration. So if it's dependent on the substrate concentration, that means it's first order with respect to the substrate and zero order with respect to the enzyme. That means you have put enough enzyme in there for the most efficient measurement, so it won't be impacted by the concentration of enzyme, it's impacted by the concentration of the substrate. So you will be here. You want to work where it's linear, where you see change in velocity linear proportional to the change in concentration of substrate. So you want to be here. Now, on the other hand, when you want to measure enzyme activity, like lipase, lipoxygenase, rennet, you don't want the substrate to be limiting. Okay? You want to have an abundance of substrate so that the reaction is really dependent on the concentration of the enzyme, because that's what you're after. That's what you're determining. So you want to be here. So you want to be where the substrate is much greater than the Km. So you want to be here. So here, you're zero order with respect to the substrate. So as you change the concentration from 10, say, to 20, you're not seeing any impact on the velocity. So it's not impacted by the substrate. So zero order with respect to substrate and first order with respect to enzyme. That means if you have higher lipase in one sample versus another, you will be able to detect the difference in concentration. Okay? So this is when we're measuring enzyme, and this is when we're measuring substrate. So in order, if we want to determine the Km and Vmax values, The only way to do it is to have an equation of the line, really. When you plot velocity over substrate, you want to try to get an equation of the line. But we don't like to work with anything not linear. So it's best to make it linear. In order to make it linear, you can invert it. So you invert, instead of velocity over substrate, you do 1 over velocity and 1 over substrate concentration, then you end up having an equation, a linear line, an equation of the line, where the slope, rise over run, is Km over V max, and the intercept is 1 over Vm. So when you get the equation, you can get the intercept, you calculate Vm, and you have the slope. You can put the slope here and Vm here, you get the Km. So it's pretty straightforward. You can get any enzyme reaction. You will be able, if you have to make sure that you're working with a concentration and you are collecting data at the steady state here. So then you can plot and determine your parameters that are important for your setup of any enzymatic reaction. Okay. So the impact of enzyme concentration, so if we have abundancy of substrate, then it is first order with respect to the enzyme. So we see an increase in velocity proportional to an increase in the enzyme concentration. So as the enzyme concentration increases, velocity increases in a linear manner. However, if we have to design our experiment, we don't want to say, okay, I want it to be fast, let me choose the highest concentration possible. If you do that, then in 5 minutes or even less, maybe in 10 seconds, you'll start seeing a depletion of the enzyme. And then your prediction line, the linear prediction line, no longer matches the actual. So we have to say, okay, I need to work with a reasonable amount of time. I need time to mix my sample. I need time to transfer it to a cuvette, to read an absorption. I cannot work in 10 seconds. So I have to choose a concentration and time that allows the prediction line to match the actual data. So I would say, okay, I'm comfortable with a 15 minutes reaction time. I will be able to complete. Then I'm going to choose the substrate concentration 2 and go with 10 minutes and get good prediction of my rate of the reaction. So other factors that impact the rate of the reaction, obviously, is the temperature. You all know that there are optimum temperature for enzymes, right? And every enzyme will have a different optimum temperature. So basically, as you increase the temperature, you will have higher velocity. Okay? However, you reach to a point where the velocity all of a sudden drops. Why is that? Walter? The enzyme degrades, it's basically denatures. That's the word that I'm looking for, but still, because it's a protein. So it gets to a certain temperature and denatures. And every protein has different denaturation temperature. Therefore, every enzyme will have a different optimum temperature. Okay. pH. So again, every enzyme will have an optimum pH. Why is that? Because when you have your substrate in a solution and you control the pH using buffer and you put the enzyme, then you are maximizing interaction of the substrate with the enzyme if you have charges. Okay, so you might want it to be charged, you might not want it to be charged, and we're talking about an enzyme is a protein, so it is impacted by the pH. The charges are impacted by the pH on the protein. So you want to choose the pH that gives you the optimal charge in the active side to allow for binding with the substrate. That's why every enzyme has different pH optimum. This is, here it says pH 6, but obviously not every enzyme will have an optimum pH of 6. But again, you see here a bell, because you have an optimum, and as you go away from it in either direction, acidic or basic, you are changing the charges on that protein active site or the enzyme active site. So you will lose activity. The activity will be reduced. But you need to know that pH stability is different than pH optimum. So an enzyme can be stable at very low pH, for example, but is inactive. But some enzymes, if you put them at pH 1 or 2 for a long period of time, you will inactivate them irreversibly. But so there is a difference. So it could be that the enzyme is still alive or still not denatured at pH 4, but it's not very active. You have to get it to its pH optimum to be active. So here's an example. Trypsin is stable at pH 3, yet optimum activity is at pH 7 to 8. So the enzyme can be alive, I would say, but not necessarily active. Yes, Sam?
So if it can be inactivated, is that if it gets more extreme pH, can it also be denatured?
Yes, exactly. So it can be inactivated if you leave it at pH 1 for an extended period of time, or pH 10 for extended period of time. You can cause irreversible denaturation, and when that happens, even if you bring it back to its optimum pH, it won't work. Heads down, everybody. Close, I would say. That was close. All right. Oh, there's a question from Lynn.
Stable means it hasn't been denatured, so it can still come back to the right condition.
Yes, so it's stable. That means if you put it at pH 4, it's still alive, it's stable. Bring it back to pH 6, it can work again. How many did she have already? Okay, butterscotch. Butterscotch, small one. Okay. So other factors that impact enzymes, activators, or cofactors we call them. Sometimes they're called coenzymes, and they can be prosthetic groups. That means groups that associate really irreversibly with the enzyme, and they're non-protein portion of the enzyme. Coenzymes, they dissociate. That means they interact and dissociate, so it's reversible. So they will enhance the activity of the enzyme. Sometimes the enzyme will not work if you don't have a cofactor. Inhibitors, again, you learn about these in food chemistry. So you have the irreversible inhibitors. Once they're bound, they are irreversibly bound. Dissociation constant is very small. That means the concentration of a dissociated inhibitor in a solution of the enzyme will be very, very low. They attach to the enzyme and they don't let it go, and the enzyme will not function anymore. And there are different reversible inhibitors that can associate and dissociate. There's the competitive, non-competitive, and the uncompetitive. You learn about these in food chem, and we'll talk about them again in chemical reactions, so I'm just going to skip that. Usually when you measure enzyme activity, most of the time, probably 90% of the time, it's based on measuring absorption using spectrophotometric methods. You can also use fluorescence. You can either measure absorption. There are some assays that you measure fluorescence. And then there is the manometric methods, titration, isotope measuring, viscosity, but all of these methods are not as commonly used as absorption followed by fluorometric method. So since most methods are absorption methods, that's what we're going to focus on. So you have your substrate, and then oftentimes you have coupled reactions. So you need the first reaction and the second reaction to get an absorption reading. So the first enzymatic reaction will give you a product, and the product you will react it with another substrate to give you another set of products. The first reaction, we call it measuring reaction or auxiliary reaction. We talked about that last time. And then the indicator reaction, because you are measuring the absorption of either the reactant, the new reactant that you added, or one of the products. And that would be what you use to calculate the concentration of the food constituents. And this example I showed last time for when you analyze for starch, you break it, for example, all the way to glucose. Then the final step, you want to determine glucose. Again, it's a coupled reaction. So you have glucose oxidase, and with oxygen, you oxidize the sugar, produce peroxide. And then the okay, this is messed up a little bit. So the peroxide will react with a dye. In the presence of peroxidase will give you water and oxidized dye, which is colored, and that's what you measure absorption of. So basically, the water and oxidized dye is the product of the second reaction. So caution with coupled reaction is because you have coupled reaction, you have two enzymes, you want to select enzymes of the similar pH. And also, this reaction, the second one, should not be rate limiting, should happen fast. As soon as you generate P1, it should quickly have very fast rate to generate P2 for detection. So these are the two things that you need to consider when you are designing coupled reactions. I'm going to stop here, continue next time.